In this video, we're going to continue talking about summarizing bivariate data, specifically talking about nonlinear relationships and transformations. So let's examine this data set where X represents the representative age and Y is going to equal the average marathon finish time. So what I want you to do is to put this into your calculator and to create a scatter plot for this data set. So you should have gotten a scatter plot that looks something like this. Now, because of the curved pattern, a straight line would not accurately describe the relationship between the average finish time and age. So since this curve resembles a parabola, a quadratic function can be used to describe this relationship. So here we have y hat equals a plus b sub 1 of x, times x plus b sub 2 times x squared. So using Minitab, the least squares quadratic regression is y hat equals 462 minus 14.2x plus 0.179x squared. Now this curve minimizes the sum of the squares of the residuals. It's similar to the least squares linear regression. Notice that the residuals from the quadratic regression are pretty small. So here's the residual plot. Since there's no pattern in the residual plot, that tells us that the quadratic regression is an appropriate model for this data set. The measure r squared is useful for assessing the fit of the quadratic regression. So here, r squared is going to equal 1 minus the sum of squares residual divided by the sum of squares total. And that's going to give us a value of 0.921. So that's telling us that 92.1% of the variation in the average marathon finish times can be explained by the approximate quadratic relationship between average finish time and age. Now, depending on the data set, other regression models such as cubic regression can be used. Statistical software like Minitab is commonly used to calculate these regression models. Another method, though, for fitting regression models to nonlinear data sets is to transform the data, making it linear. Then, a least squares regression line can be fit to the transformed data. So here's some commonly used transformations. You have no transformation of y hat equals a plus bx. You can use a square root of x, so y hat equals a plus b times the square root of x, the log of x. You can also use the natural log here. So we have y hat equals a plus b times the log base 10 of x. The reciprocal of x, which is y hat equals a plus b times 1 over x, or the log of y for exponential growth or decay. And you can also use the natural log here too. So here we'll have the log base 10 of y hat equals a plus bx. We're going to go ahead and we're going to do a transformation together. Let's go back to the pomegranate study that we talked about in a previous video, where x is the number of days after injection of cancer cells in mice assigned to 0.2% PFE, and y is going to equal the average tumor volume. So we're going to put this data into our graphing calculator, and I want you to create a scatter plot for this data set. Push pause, and when you're done, push play. So our scatter plot appears to be a curve. There appears to be some type of a curve in the data points. It doesn't really look like it's quadratic like a U, but there's a slight curve in there. So let's use a transformation to linearize the data. Now, since the data appears to be kind of like an exponential growth, we're going to try the log of y transformation. So now we're going to sketch a scatter plot of the log of y and x. When we do that, we have this scatter plot. Notice that now the relationship appears linear. So we're going to fit an LSRL to the transformed data. When we do that, notice how well it fits. So our LSRL is the log of y hat equals 1.226 plus 0.041x. What would the predicted average tumor size be 30 days after injection of cancer cells? Well, 30 days represents our x value, so we can plug that in. And here we see that we have the log of y hat equals 1.1226 plus 0.041 times 30. And when we calculate that, we have to get the y hat by itself. So we'll need to get rid of our log. So to do an inverse of a log, we'll need to take an exponential. And so we're going to have 10 raised to the 2.456, and that's going to give us a value of 285.76 millimeters cubed. So hopefully this helps with how to transform that data so that it can fit a linear regression model, and also some ideas about some software you can use when your data model, your scatter plot model, doesn't really look like it's going to be linear.